So, how many of you guys are like fans of Star Wars or know Star Wars? Have you seen the speeder bikes? So, what if I told you that those are basically real?
Makes sense.
Okay, so my project is on the Madgwick filter or the Madgwick filter, and basically what it is basically a set of computations that you input data to in order to like stabilize the speeder bike. So right now it's really common in drones, and a lot of my examples will be with drones. So a little bit about the Madgwick filter. There's this guy, Sebastian Madgwick. He's a really prominent engineer in these little sensor units that it's effectively just a box, and it's got a lot of sensors in it, and it collects a lot of data at once. And so what you do with that data is then you pass it to a computer, and that's where the Madgwick filter comes in. Is on that computer it has this program called the Madgwick filter that basically handles all that data. It makes the drone super stable. So how does it work? So basically you have this little box of sensors. It takes data, it passes it to the computer. The computer uses what are called quaternions, and I'll get into what those are. But basically it uses the quaternions and it represents them in space because there's no grid system in thin air. You have to represent the grid system basically with imaginary numbers. Imagine you're like traveling along a line, just a line segment. So this is one dimension. Everybody's familiar with 2 dimensions and 3 dimensions. So a quaternion is you have a 3-dimensional space, and this line segment is moving through it. So it gets into object rotation, and how do you track object rotation in space? You use quaternions. And how quaternions are formatted is you just have 4 numbers. So you have X, Y, Z, and W. So X, Y, and Z are just your first 3 axes, and then W is just a scalar value of how fast the object is rotating in space. So in order to keep track of a drone rotating in space, you have to use 4 dimensions, and you use quaternions to represent those 4 dimensions. The application of quaternions in the Madgwick filter is you have a lot of data being thrown into a box. The box passes data to a controller, and the controller formats that data into quaternions. And then I'll go down here to a diagram so it's just easier to see. This thing up here, this is just an equation, the mathematical representation of a quaternion, and that's how you get those 4 numbers into that little array. So this big thing, it took me a while to figure this out, but this green box, it's the mathematical representation of what's called a gradient descent algorithm. It helps just normalize values from an acceleration input. So all the inputs that are going on from the IMU, or just the box, you have acceleration data, you have gyroscopic data, and then you just have to merge those 2 together in order to get your end result. So the green part up here is your acceleration data. The blue part down here is your gyroscopic data, and those are both each their own quaternion. So those are both line segments moving through 3-dimensional space. You take these 2 parts, you multiply them together to get what's called a quaternion product. So that's like the end result. The end result is going to be a single quaternion. So you're going to get a new line segment moving through 3-dimensional space. And then from that line segment, you get roll, pitch, and yaw values using these equations. So this is a quaternion. This is multiplying individual quaternions, and then this is extracting roll, pitch, and yaw values. And roll is this motion, pitch is up and down, and yaw is turning from side to side. So from there, you can translate those values into controlling a drone. To implement this Madgwick filter, well, you got to write some code on a controller. So all the code is doing is looping over and over again, because you can't just do one calculation and then stop. The drone's going to fall out of the air. You got to start a timer because the drone is moving through space over a period of time. So you have to take multiple snapshots of data of where the drone is in order to predict where it's going to be so you can correct it. And that's how the stabilization works. So you start a timer, and then you get a snapshot of where the vehicle is. Then you compute where you want the vehicle to be, and then that's where you pass it through all the Madgwick filter stuff. And then you extract roll, pitch, and yaw values, and then you basically translate those values into something that the drone's motors can understand, and then you just send that to the drone motors. Going into the radio commands, just looking at this diagram here, the main loop, all it's doing is taking data from the IMU, converting it into something the motors can understand, and then it also listens for radio commands. So it merges those two things together so that the drone can fly. And then it just repeats the process. So this is part of the code for how you would actually write commands to the microcontroller. So the commands being written to the microcontroller are just what it's going to be doing over time. So a bunch of these functions you can see, well, I guess you can't really see it, but this is just calling the IMU data.
Is Bluetooth to your compiler? How do you get this to that?
So how it's set up.
I'm very interested in how this information is traveling around these things.
So the code you compile isn't transmitted over Bluetooth. I probably should have brought like a prop.
You just link it right into the brain of the drone?
Yes.
Oh.
So you usually have your computer connected over USB to the microcontroller.
Okay.
And then you do what's called flashing firmware. The computer takes care of all the compilation, then you load it onto microcontroller, then you can unplug it, and then your drone's ready to go.
It outputs it in whatever language that speaks.
Yes.
Yeah, that's cool.
So this is in C++, and I don't know, has anybody used Arduinos?
Yeah.
Okay. All right. So you use something along the lines of an Arduino, and that's just a microcontroller to control the drone. And this is some of the code that is used to apply the Madgwick filter and get all the data and do what I explained earlier. So some other functions are control mixing. So you can have different kinds of vehicles. It doesn't just have to be a drone. It could be a jet that flies in like a forward motion instead of a vertical like hover motion. So you have to mix the commands in a certain way from your controller so you can actually control the vehicle and not crash it. So this is just some of the code that is used.
Do engineering majors here have to take C++? For my math degree, I had to take a programming 1 and 2. Is that a requirement for their degrees here?
I don't think from a
Our math does.
not from
Mechanical engineering. Not from what I saw.
All right, so I got 2 videos. One is an implementation of a hobbyist. So he made like a little jet. I've been talking about how you could set up a drone, but he used a jet. This is the video. It must have already played. Let's see. Okay. So after you compile all the code on your computer and load it to the drone, then this is what you can do controlling it with a little radio controller. All right, and then this is a scaled up version where people can actually ride in drones. So instead of a radio controller, you sit in the drone.
More scary.
Yeah.
Terrifying.
Yeah. So you take out the radio controller and you put that in the cockpit.
I don't like driving 60 miles an hour in 6 inches of snow. I cannot imagine hopping in an Anakin Skywalker little thing flying around the desert. Yikes.
That's pretty cool.
They'd be like, this lady's passed out in this cockpit.
Can it go faster?
How do you know the cost?
You could probably Google it. I don't know. This might be a prototype. This whole presentation is kind of about the Madgwick filter, but really I wanted to make it about you can flying a drone. Yeah, but yeah, the Madgwick filter, it's just a computational function. So you get data, you pass that data to a controller, the controller uses the Madgwick filter to do a bunch of computations on it, and then it translates the values that are the result of that computation to something the motors can understand. And then that's how you keep the drone stable in air.
So where did you find calculus one stuff in this?
So, let's see. So if you go to this diagram, it integrates it right at the end.
It works.
I think I
Okay.
saw like at least one duration too.
Yep. So, yeah, that's the Madgwick filter, and that's my presentation.
Can I steal a